So section 7.3, one sample test for the mean. Okay, so in this section we're going to be dealing with quantitative data. So it's time to go back to look at the test for the mean that was introduced in section 7.1 called the z-test. So although we walked through a really long problem with lots of steps trying to bring those first 6 chapters together, we actually didn't do any problems like that in the homework. Because in that example, you knew what the population standard deviation sigma was. But typically we don't know the standard deviation. So in that section we ran through the z-test for the mean because it tied nicely to the normal distribution that we had just finished in chapter 6. But most of the time we don't know the value of sigma, and it turns out in that case that the normal distribution doesn't quite give us the right probabilities. So usually we do not know the value of sigma since it's the population standard deviation. So usually all we have is a sample standard deviation, which is the value of S. So you could just use the sample standard deviation as an approximation of sigma. So that means we'd get this new test statistic of x bar minus mu, and instead of sigma over root n in the denominator, we would have S over root n. So great, now you can go and you can find the p-value using the normal curve. Or can you? In this new test statistic, is this new test statistic really normally distributed? Well, at one point in time it thought it was, and it was used that way, but it turns out that small samples don't give us a good enough approximation for sigma to be able to use that distribution. So actually it's not. So how is it distributed? So a man named W.S. Gossett figured out what this distribution is, and he called it the student's t-distribution, although we're just going to call it the t-distribution as it's normally referred to. There are some assumptions that must be made for this formula to be a student's t-distribution, and these are outlined in the following theorem. But little side note here. So the t-distribution is called the student's t-distribution because that's the name he published it under. So, he should have called it like Gossett's t-distribution, but he didn't. He just used the generic name student, so student's t-distribution. Because his employer didn't want him to publish under his own name. So his employer, by the way, was Guinness, as in Guinness beer. So now it might make some sense as to why he had to use small samples to be able to still function throughout the day and to do his job. And they didn't want competitors knowing that they had a chemist working for them. So it's not called the student's t-distribution because it's only used by students. That's just the name that he happened to publish it under. But as I said, we're just going to call it the t-distribution anyway. So we have a theorem here that looks very similar to something we used in chapter 6 for the normal distribution, only slightly altered to use this t-distribution instead. So again, we're going to assume we took a random sample of size n, and the distribution of the random variable that we start with either has to be normal or the sample size has to be at least 30. So we had this condition back in chapter 6 as well. So we either need a normal population or n has to be at least 30. And we don't want any outliers in the data set. Like I said, in this intro course, we're just not going to deal with how we deal with outliers. So then the distribution of this new standardized score, instead of using a z-score, looking at a t-score, follows a t-distribution. And we can then use that to get our tail probabilities and p-values for our hypothesis tests. Now, this thing also has something called degrees of freedom associated with it, but since we're using technology and no tables, we're not going to worry about what that even means for this particular course. So a t-distribution curve looks a lot like a normal curve. It's another bell-shaped curve that's symmetric, single mode here, except it has slightly fatter tails. Which means the tails are fatter, which means as we're getting the area in those tails for a right-tailed test or a left-tailed test, that area is a little bit bigger than had we used the normal distribution. So as you can see below, the degrees of freedom actually related to sample size. As the degrees of freedom increases, the t-distribution gets closer to the shape of a normal curve, which is why in many fields, like in sciences, where they collect hundreds, thousands, sometimes millions of data points, they just use the normal distribution always, whether they know the value of sigma or not, because they have such a large sample that their approximated value of S is is well approximating the value of sigma. Now, your calculator has some built-in functions with TCDF and inverse T functions on it, but we are not going to use these in this course because they're automatically programmed into the t-test to get the numbers that we need.